Hi, Fox. So right now we are going to continue our topic regarding with the data management. We're done with the measures of skewness already, and right now we're gonna continue discussing about the shape of our distribution of all our data observation. And in this topic, we're going to talk about the kurtosis or the measures of kurtosis. So we need to know what is kurtosis and how to compute for kurtosis and how to interpret the shape of the distribution given the measure of kurtosis. And first, top in line, of course, we need to take a look what is the definition of the kurtosis. Kurtosis is the measure of bigness of a given distribution. So it measure the degree of how more or how less the bigness of a normal given distribution. And the larger the kurtosis, the more big will be distribution. Will be the distribution. Just like the skewness, the larger it takes away from the zero, or the larger it has been skewed as well. So for this, there will be also an interpretation that you can be able to determine the shape of the distribution once we got the result for finding the measure of kurtosis. So there will be a formula as well that we can use to find out what will be the shape of the distribution. Of course, the concept of kurtosis is very useful in decision making, especially for conducting a research. And just like the skewness, we have three categories of distribution. So first in line we have the leptokurtic distribution. It is more big than the normal distribution. As you can see, it's really high. So the higher peak results from clustering of data points along the x-axis. The tails are also higher than those of our normal distribution. And the coefficient of kurtosis is usually found to be more than 3. Okay, so if you already compute for the measure of kurtosis, you use the given formula and then you get the result of greater than 3, then our observation is leptokurtic distribution. And the term lepto means thin or skinny. So when analyzing historical returns, a leptokurtic distribution means that small changes are less frequent since historical values are clustered around the mean. So however, there are also large fluctuations represented by the fat tails. Alright, so we're done with the leptokurtic and we're going to talk about the mesokurtic. Mesokurtic is the normal distribution itself. It is somewhat similar if you remember on the shape of the distribution when we're talking about the skewness. It's almost similar to like a symmetrical distribution. Okay, so mesokurtic distribution have a curve that's similar to the normal distribution, as I mentioned. So in other words, the distribution is largely normal. Okay, and when you compute for the measure of kurtosis, it is always equals to 3. So our base will always be 3. Unlike in the skewness, our base is always 0, right? You're just getting, if you get a negative, then it will be a left tail distribution because you got a negative number less than 0. But if it equals to 0, then it is a symmetrical distribution. When you get greater than 0, then it is a positively skewed distribution. So for this, again, for the leptokurtic, if you get greater than 3, then it is a leptokurtic. But if you get similar to 3, equal to 3 value, that is mesokurtic. And let us talk about now for the platykurtic distribution. So this has a extremely dispersed points along the x-axis, resulting to a lower peak when compared to the normal distribution. So platy means broad, as you can see. Hence, the prefix fixes the distribution shape, which is wide and flat. Okay, so from the word platykurtic, it's flat. The points are less clustered around the mean compared to the leptokurtic distribution. So the distribution is more spread out than the leptocortic. So the coefficient of kurtosis is usually less than 3. Okay, so the base is also 3, so when you get the less than 3 value, that means that the distribution is bradycardic. So returns that follows this type of distribution have less major fluctuations compared to leptocortic returns. You should note that fluctuations represents the riskiness of an asset. So more fluctuations represent more risk and vice versa. Therefore, bradycardic returns are less risky than leptocortic returns. Okay, so we're done with interpreting with the shape of our distribution. Let us move forward to the formula that we are going to use. Okay, so how are we going to get the measure of kurtosis? We're going to get that using this formula, K, kurtosis is equals to 1 over n times the summation of the quantity x minus mean raised to 4 divided by the standard deviation raised to 4. So K is the denotation for kurtosis, N is for the size of the distribution, or somewhat called the total number of our data, and X will be each data on a set. And X bar or mu, this one here, X bar and mu is the same. Okay, you're getting the average or you're getting the mean. And this one here is the symbol for the standard deviation. And again, this is our formula for getting the standard deviation. Alright? We just always remember that. And I'm going to introduce to you those interpretation. When the distribution is normally distributed, its kurtosis is equals to 3 and it is said to be mesocortic. Okay, so it means that our distribution is symmetrical or a normal distribution. If you got the value of 3 once you use the formula for finding measure of kurtosis. But if ever we have the distribution that is less spread out, its kurtosis is greater than 3 and it is said to be leptocortic. Okay, and what if we have the value that is less than 3? Okay, so when the distribution is more spread out than normal, its kurtosis is less than 3 and it's said to be bradycardic. Okay, so just bear in mind this interpretations in order for you to get what is the shape of our distribution if ever we're talking about the measure of kurtosis. So let's have the first example here. The monthly salary in dollar of 7 employees in a factory are given below. So we have $230, $180, $325, $220, $315, $405, and $108. And from this set of example as of the moment, you can be able to determine the summation or the total of it. Just add all of those, and then from the given problem itself, it says here that we have 7 employees in a factory, so it means that our n will be 7, or the size of our distribution is 7. And first off, of course, we need to determine what is the mean of our distribution. So use the summation of x divided by n. Summation of x means that we need to get the sum of all of the given data divided by the number or the total number of data. So as you can see, we have 1,855 as our total, and then our n is 7. So 1,855 divided by 7 is 265. So that will be our mean. And then we can move forward now to our next table. So we're going to get the difference between the each of the data in a set and as well as the mean. So 230 minus 265 is negative 35. 180 minus 265 is negative 85. 325 minus 265 is 60. 220 minus 265 is negative 45. 315 minus 265 is 50. 405 minus 265 is 140. And 180 minus 265 is negative 85. And on this part, of course, the second column, as I mentioned, the clue here is when you are getting the summation of all this differences between each of the data set in the mean, you should be getting 0. So if you get 0, it means that you got the right differences here. Alright, and next up, for the third column, we're going to get the squared of those computed value for the difference of the mean and as well the data on, each of the data in a set. So we're going to square this. Why? Because we need to get the value for the standard deviation. And you know already that the formula for getting the standard deviation is the summation or squared of the summation x minus mu, or the mean, squared over n. Alright, so let us square this. 35 squared is 1225, 85 squared is 7225, 60 squared is 3600, 45 squared is 2025, 50 squared is 2500, 140 squared is 19600, and 85 squared is 7225. And now we're gonna move forward in getting the fourth moment in our fourth column. So we're gonna get and then raise it to the power of 4, these differences. So here, okay, we got the summation already here, so it will be easier for you. So we got the total of 43,400. And yes, as I mentioned in the fourth column, we are going to get the fourth moment for this distribution. So 35 raised to 4 is 1,500,625. For the 85 raised to the fourth power is 52,200,625. 60 raised to the fourth power is 12,960,000. 45 raised to the fourth power is 4,100,625. 50 raised to the fourth power is 6,250,000. 140 raised to the fourth power is 384,160,000. And then again, the 85 to the fourth power is 52,200,625. So we're going to get as well the summation for this. And the total for all of this in the fourth column is 513,372,500. Okay, since we already got this information right now, so we're going to solve for the standard deviation first here. And our n again is 7. And use this formula for getting the standard deviation. The squared of the summation x minus the mean squared over n, the size of our distribution. And yeah, just substitute. We have the square of 43,400 over 7, or divided by 7. And 43,400 divided by 7 is 6,200. So get the square of 6,200, we have 78.74. So bear in mind, if you're getting the decimal number, just always round it off to the nearest hundreds. Alright, so after we get the standard deviation, substitute and then solve. So given this formula for getting the kurtosis, so just substitute all of the values that we have already computed. So we have kurtosis is equals to 1 over 7 times 513,372,500 divided by 78.74 raised to the fourth power. And the 78.74 raised to the fourth power is 38,439,846 and 24. Okay, 24 hundredths. And so we're going to multiply this denominator to 7, and we got this equation of kurtosis is equals to 513,372,500 divided by 269,078,923 and 70 hundredths. So when we divide this, we're gonna get 1.91 as our kurtosis. And from our interpretation, so when you get the value of k that is less than 3, it means that the shape of our distribution is platykurtic. So that's how easy it is. Just always be careful when you are solving for the kurtosis, because I bet you have a lot of course ways and steps in order to get to the final answer and in order to get the right shape of the distribution. Now let's move forward to the next example. Given the following vegetables in kilograms of Aling Martha's store, we have 26, 12, 16, 56, 112, and 24. So we need to complete the measure of kurtosis. And then, yeah, we have n, which is 6. So we have the total number of our data is 6. And then, given our table already right now, so it's already been plotted here so that you can be easily solve for our measure of kurtosis. And we're just going to get the mean first. So our total for this is 246. So we divided by 6 is 41. Okay, this one. So first, of course, you need to get the summation or the total or add all of those data here. So you get 246 divided by 6, which is our n, and then our mean right now, or our mu, is equals to 41. Since we have the mean already, we're going to get now the difference between each of the data set and the mean. So we have 26 minus 41 is negative 15, 12 minus 41 is negative 29, 16 minus 41 is negative 25, 56 minus 41 is 15, 112 minus 41 is 71, 24 minus 41 is negative 17. And just get a summation of this in order for you to check. Alright, so the summation will be 0. So it means that we got the right differences here. And next in line, we're going to square this value. So 15 squared is 225, 29 squared is 841, 25 squared is 625, 15 squared is 225, 71 squared is 5041, and 17 squared is 289. And in total, we have 7,246. And next step is we're going to get the fourth moment here. So 15 to the fourth power is 50,625. 29 to the fourth power is 707,281. 25 to the fourth power is 319,625. 390,625. And then 15 raised to the fourth power is 50,625. 71 raised to the fourth power will be 25,411,681. And then 17 to the raised to the fourth power is 83,521. So get the sum of all of this. We're gonna get 26,694,358. So after we get all of this value, then we're gonna move forward and solve for the standard deviation first. Again, our n is 6, and substitute the given summation of x minus the mean raised to the 2, or mean squared, and then also the 6, which is for the n, so substitute that one. So we're gonna get the square of 7,246. Okay, and then divided by 6, we're gonna get the square of 1,207.67. And once we get the square root of this, we'll get the standard deviation value of 34.75. And then substitute and solve using this formula for getting the kurtosis, or measure of kurtosis. So we're gonna have the equation of k is equals to 1/6 times 26,694 26,694,358 divided by 1,458,207.19. So why we got this already? Because we got the fourth power of this 34.75. So this will be the resulting value. Alright, and then we're gonna multiply 6 to the denominator, and we're gonna get 26,694,358 divided by 8,749,243.14, or 14 hundredths. So make sure that when you're getting the decimal number, make sure it will be round off to the hundredths, okay? And once you solve this, you are gonna get the value of 3.05. Okay, our measure of kurtosis will be 3.05. It means that we get the value that is greater than 3. So if k is greater than 3, then the shape of our distribution is leptokurtic. Okay, so that will be all, and thank you so much, right? And God bless you. Okay, bye-bye.